My presentation today is on probabilistic service life modeling and more specifically validation case studies of a service life model that is diffusion based. So the presentation going to include a little bit going over the service life modeling basics and why do we need validation studies. I'm going to then describe the description of the structures that are included in those validation case studies and go into how we perform in-depth corrosion assessment in the field and how do we evaluate the chloride diffusion behavior and also provide some introduction to the service life model that was used on those studies and share the results and finally the conclusions. So corrosion, as we all know and might be interested in by attending this session today, is one of the main degradation mechanisms that we see in reinforced concrete structures. And service life modeling for corrosion damage is becoming one of the hot topics because it provides significant value in understanding the future performance of the structure, and we can use that for durability design for new construction. So it can help us with material selections to achieve durability goals. But we also use it for estimating what is the remaining service life for existing structures. And that can help with lots of rehabilitation planning and even, most importantly, optimize the timing for repairs. So why do we need validation studies? So we have service life models. The model gives you what is estimated damage that you're going to see over the surface area of your structure with time, and based on that you can get the remaining service life. But if our models are not accurate, we might end up with an overestimated damage, predicted damage, and that might have implications on the rehabilitation planning because you will end up with more aggressive recommendations for repairs, and it's going to lower the cost effectiveness of the rehabilitation plan. On the other hand, if we underpredict the damage, we will reach the end of the service life before what was predicted by the model, and that would create lots of problems with the funding allocations and the goals for the rehabilitation. So to be able to develop cost-effective asset management plans, we need accurate models. And to get accurate models, we have to validate them to make sure that the models that we are using are appropriate for the deterioration mechanism and the structure that we are modeling here. So because of those reasons, we performed those case studies for bridges in the Midwest. The case studies that I'm included here are also presented in a paper that's going to be published later this month as part of the AMP proceeding. So our case studies included two structures. So we have a series of bridges along the I-94 Kennedy Expressway in Chicago area. So we investigated the performance of 7 bridges along that stretch in Chicago. And we did the investigation back in 2011, where we did all the field corrosion assessment and collected material samples, and we did service life modeling to predict the performance in the future. But then we went back to the same bridges in 2023, and we did the investigation again, and we collected more core samples to look at the chloride profiles and how it advanced over this 10-year period to use as a validation for our predictions. And we did the same thing for another bridge in Indiana State Route 46, where we went back in 2013, we did the field investigation, collected cores, did service life modeling, and then we redid that in 2024 to validate the modeling results that were done 10 years before that. So going a little bit in detail on the structures that we investigated here. For the Kennedy Expressway, those bridges were constructed in 1992. They didn't have overlay, and based on the initial investigation in 2011, these bridges showed typical transverse cracking. We did GPR scanning, and the concrete cover was in the range between 2.2 to 2.8 inches on the 7 bridges. So this is the average value for over the 7 from the different bridges that we included in that study. And this is typical of IDOT construction. So typically IDOT specifies 2.5 inch of cover for bridges. And when we did the investigation in 2011, the damage that we have seen, which is lamination and spalls of the concrete cover, range between 1 to 5% of the surface area of the bridge deck. When we went back in 2023, that damage percentage increased over those 12 years to 4 to 21%. So we had range of condition over the 7 bridges. Some of them were as low as 4%, and some were as high as 21%. So the other bridge that was included in the validation study is a post-tension structure. This bridge included sacrificial latex modified concrete overlay of 2 inches. So that was the substrate that it included 5 inches of total cover over the reinforcing steel. This one, when we did the investigation initially in 2013, we didn't find much cracking. There were limited cracking around the joints, but there wasn't widespread cracking like the other bridges. And the damage in general was pretty minimal in 2013, and even in 2024, it didn't increase that much over the 10 years. So for each of those bridges, when we did the field investigation, we did a combination of visual assessment, and we did sounding survey to identify areas where we have delaminations of the concrete cover. And we also did non-destructive testing. So we included half-cell potential testing, resistivity testing, to learn more about areas that might have had corrosion initiation, but it's not showing delamination or spalls yet. And we also collected concrete cores at representative locations to look at the chloride profiles and test them petrographically to learn more about the concrete mix that was used for those bridges. And then for each of those field investigation, we mapped our observations on digital field sheets, like seen here on the top left of the screen. So we mapped all the cracking. This is kind of the limited locations of the lamination and spalls that we've seen. And for example, one of the bridges along the I-90 bridges here, Irving Park. So in 2011, there wasn't that much damage, so they are shown in gray here. But when we went back in 2023, the delamination and the spalls has increased a lot. So you can see how much the damage has increased over those 12-year period between the two investigations. One of the things that we also wanted to look at is how the chloride profile changes, and to efficiently do that and to be able to eliminate some of the variability that we anticipate over the surface exposure, we collected what we call replicate cores. So we went back to the locations where we collected cores in 2011 or 2013 for the other bridge, and we collected cores right adjacent to that, so within few feet, to look at the chloride profile and be able to investigate how much more chlorides got into the concrete over this about 10-year period between the two investigations. So next I'm going to go briefly over what is the diffusion behavior that we have seen based on those chloride profiles. So for each of the cores that we collected, we sliced it at predetermined depth from the surface of the concrete, and we tested it for chloride concentration, so water-soluble or acid-soluble chlorides. For this test, we used acid-soluble. And we looked at how the chloride concentration changes with the depth from the surface. So here is one example of one of the chloride profiles. You could see it goes higher at the surface and then it decreases as you get deeper. This is consistent with the diffusion behavior from the surface. So we learn a lot from those chloride profiles. We can run the diffusion fit and we can learn what is the diffusion properties of the concrete. And we can also extend that to the surface and see that curve to the surface and learn about what is the surface chloride concentration that the structure is seeing at that location. We also look at what is the chloride concentration at the bar depth and compare that to the chloride threshold to learn more about the probability of corrosion initiation at that location. So there is a lot that we can learn from those chloride profiles, and this is why it's important to collect enough cores to be able to capture that variability that you expect over the surface area of your structure. So here's the data of the chloride concentration from the SR46 bridge. So this data on the left here is from 10 uncracked cores that were collected from that bridge. And as you can see, the concrete was contaminated over like the 1 to 1.5 inch of the concrete cover, and basically within the overlay, the latex modified overlay that was present on that bridge. But beyond that, there was minimal chloride concentration. So in the substrate concrete, beyond below the overlay, there wasn't much chlorides that got into the bridge deck at an age of 25 years. And also, of course, at the bar depth, based on that, we don't have much chloride concentration as well. So the risk for corrosion initiation was identified as very low at those locations. One of the interesting things that we wanted to look into too is the effect of cracking. So we collected also some cracks at some cores at cracked locations, and we looked at the chloride profile. And as you can see here in the curve in orange, this is a cracked core. The chloride concentrations were much higher compared to uncracked locations. So those are two locations actually adjacent to each other. One of them is at a crack and the other one is uncracked. And this highlights the importance of accounting for the cracks when you evaluate the durability of your structure, because those cracks can facilitate the chloride penetration and can cause corrosion initiation earlier than uncracked locations. And it's important to consider that in the model. So one of the things that we looked at during the field investigation is to characterize what is the crack density that we have in the structure and account for that in our model when we predict the performance. And then looking at the replicate cores. So remember those cores where we went back later, 10 years later, and we collected cores right adjacent to the older ones to see how the chloride profile changes. And we have seen typically performance similar to the left figure here, where we have seen that the surface chloride concentration didn't increase much, considering also the age of the structures when we did those investigations. But the chloride concentration over the concrete cover has increased over those 10 or to 12-year period between the two investigations. So you can look at the total chlorides as the area under the curve, and you can see the increase there. At some locations, there wasn't many of them, but at some locations, we have seen that the surface chloride concentration actually increased between the two investigations. And here I picked this profile specifically to highlight how important, the interpretation of those chloride profiles. Because the figure on the orange here, as you can notice, the second slice was a little bit higher in concentration than the one closer to the surface. So this happens due to wetting and drying, and we call that zone convection zone, and there are different ways to account for it. So if we ignore that and we continue with the diffusion fit, you get much higher surface chloride concentration. So, but another approach is to consider that convection zone and consider the highest value here, or the peak value, as a surface chloride concentration, and account in your model for that convection zone affected by wetting and drying. So there are different ways to consider chloride profiles in your model input, and you have to be careful about how many of your profiles represent a specific condition, and you can make the evaluation whether it's worth considering in your model and how to consider it. So that was talking about the local kind of performance at the core locations. But looking more globally at the performance that we have seen between the two investigations, so over that, the change over that 10-year period between the two investigations of the bridges, and looking at the average chloride profile. So looking at the chloride profiles from all the cores and plotting an average from all of those from 2011 and then again from all the cores that were collected in 2023 over the same bridges, and looking about how that chloride profile it changes. We see that the surface chloride concentration here, as an average of over all the cores, it didn't change that much. There was increase in the chloride concentration as expected. For the SR46 bridge, that increase was about 18%, but for the I-94 bridges, that was on average about 24% increase in the total chloride concentration over your concrete elements. So to be able to speak to how we consider the variability and in those case study of the input parameters and service life modeling of those case studies, I wanted to first provide kind of a brief introduction to our modeling approach here. So we did our model using our in-house service life model, WJE Castle. And this is based on Fick-Second law of diffusion, which considers the time it would take for the chlorides to build up at the surface, and then how long it would take to diffuse over the concrete cover until it reaches the bar, and then accumulate at the bar depth to a concentration that we call chloride threshold. And this is when we consider initiation happens at the corrosion, and the corrosion starts of the bar. And then how long after that it takes for the corrosion product to build up and cause cracking and then the lamination and spalling of the concrete cover. So one of the important considerations is that chloride concentration, or this critical concentration that we consider for corrosion initiation. So for those models, we considered for the uncoated bars, the beta distribution that is based on literature review of different sources, and this is basically have a mean value of 0.48% by weight of cement. This is kind of in general within the same range that was found from the study that was recently done by the 222 committee to develop a standard test method for the chloride threshold. So that study found about the mean value from the round robin testing was 0.4% by weight of cement. So it's pretty consistent to what we use here based on the literature review. And then for epoxy coated bars, we use a higher chloride concentration to account for the benefit of the epoxy coating. And this distribution was developed based on field investigation on over 45 bridges in the Midwest region, mainly like Iowa, Wisconsin, Illinois, and also some bridges in New York and Michigan. So based on those investigations, we developed that statistical distribution. If you want to learn more about it, you can refer to that reference paper here. But overall, we consider the time to damage at that summation of that time to initiation plus that propagation damage. So how the model considered that? It considered small subset of your element, and over those it models the performance, and to get the time to initiation over those small subset of your elements. And based on that, and considering all the variability of your input parameters, we get what is the percentage of damage with time. So we consider the concrete cover and the variability of that based on the field investigation, the diffusion coefficient and the exposure based on the chloride profiles that we have seen from the different cores, and then the chloride threshold that I showed the distributions of a little bit ago. And based on that, we get what is based on those different distributions, we get the time to initiation of those little subset, and based on that, the overall percentage of damage with time. Typically, when we do service life modeling, we want to verify the results, and typically when we do the investigation at an age from a construction, we do also the field assessment. So we collect data on what is the percentage of damage that we are actually seeing on the structure and compare that with the predicted value to verify our models. One of the other methods that we can do is also half-cell potential testing. So half-cell gives you what are the area with high, how much of the areas of your structure that have high probability of corrosion initiation. And you can compare that to the predicted value of corrosion initiation at the current age and be able to verify your model for initiation time. So ideally, we perform that at different points in time, but at least we want to verify our model at the current age. But to take it a step further, we do the validation study similar to what we did in the case studies here, where we go back after a number of years and compare what are the actual damage percentage now versus what was predicted a number of years before. So getting into the results from the service life modeling validation here. So we looked first at the distribution of the different input parameters. So for example, here I'm showing on the left the parent diffusion coefficient values that we have seen from the bridges along I-94, and on the right for the surface chloride concentration. And it's important to plot the data and look at the variability over your surface area of your structure, and based on that, select the best fit for a distribution to best represent that modeling input parameter. So it's not necessarily a normal distribution. It can be log normal, Weibull distribution, or beta distribution. For this study, we used a combination between normal and log normal distributions based on the distributions that we have seen for the different input parameters. One of the exercises that we wanted to look at is the effect of the sample size. So from the I-94 study, we collected over 40 cores at uncracked locations in 2020, in the investigation that was done in 2023. So we wanted to see what if I randomly downsize that sample, how the average surface chloride concentration can change. So going down from the 40 cores down to 25 and then 18 and 7 cores, how that average value using different combination of random sampling from out of those 40 cores, how that would change. And as you can see here in the figure, the smaller number of samples you have, the wider range of average that you can end up with from your cores. So it is important to collect enough cores that represent the overall variability of exposure conditions on your structure, because otherwise you might end up with a skewed input parameter that gonna result in misleading results for your predictions. So this highlights kind of the importance of the sample size as well when you're planning for the corrosion assessment. So going into the results of our validation, for starting with the SR46 bridge, so this is a bridge that had the overlay and thicker concrete cover. We have seen very strong correlation between the field observed damage and the model predicted damage. So overall, the damage over this bridge was pretty low because of the thick cover and the overlay that was present. But when we use the model inputs from 2013, and the predicted amount of damage agreed a lot with the field observed damage, and also the prediction for ages of 25 years, starting from the inputs that was collected at 2013, also showed good correlation at the 0.3 value here against 0.1 that we observed in the field. And then updating the model with inputs from 2024, that updated the results a little bit and actually predicted higher on the, a little bit higher on the, at the current age at 25 years of age. But overall, those are very low values, and maybe it's not, provided a good value of validation, but we wanted to see what if we have bigger percentage of damage, how accurate is the modeling results? And we have that opportunity with I-90 bridges because those bridges were in worse condition. So actually, when we did the investigation in 2023, those bridges were due for overlay and installation. So we talked with the IDOT, and we told them, like, okay, this is a good opportunity since you're going to have the traffic closure. We want to come and we're going to do the investigation and collect the cores, and this is going to be an opportunity to validate the modeling results that we gave you more than 10 years ago. So this is how we got the opportunity for the validation study. So looking here at the series of bridges where we had much more damage compared to the other one, when we used the model inputs from 2011, so ignoring all the data that we collected in 2023, we predicted at an age of 19 years, which is the age of the first investigation, 1.8%, compared to the 2.2 that we actually see on the structure. So this is pretty good agreement between the predictions against the actual damage that we have seen on the structure. Then if we use also the inputs from 2011 and predict forward to the age of 31 at the second investigation, we got to 9.9, so almost 10% against the 13% of field observed damage. So we were within less than 3% of the actual performance of the bridge. And we updated the model using the 2023 data, which enhanced also the results a little bit as expected because you're kind of calibrating, adding another calibration point. So overall, those results showed really good agreement with the field observed damage. And one thing to note that most of this damage actually was at crack location. So this highlights the importance of considering cracking and how significant are the cracks to the performance of the structures. So going into the conclusions here, our first conclusion was that the finite difference solution that's used in the model that was used in these studies to fix second law of diffusion is an appropriate representation of the chloride ingress. And we've seen that based on the chloride profiles that we collected at different ages, and also as implied by the percentage of damage, which was within 3% from the observed damage in the 2 case studies. Also, when we started with the predictions from based on inputs from the initial investigation more than 10 years ago, we ended up with really good agreement with predictions against the actual damage at the 10 years after. So this kind of gives a validation that the model input parameters that was collected and how we interpreted it like more than 10 years ago provided acceptable accuracy for the service life modeling and predicting the performance of the structures. Also, it's very important to study the variability of some of the input parameters, especially here from those studies. It was the surface chloride concentration and the diffusion properties of the concrete. So we noticed lots of variability even within the same structure, and it's very important to accurately characterize that and carefully plan your field investigation and the collection of cores to be a representative area to capture that variability. So at the end, I would like to thank you, and here is also a reference of the paper that's not published yet, but it's going to be published next month if you're interested as well.